welcome back to my course Aspects of Biochemical Engineering. Last couple of classes mostly I discussed the theory part of enzymatic reaction kinetics. We try to explain what do you mean by enzymes, how the enzyme substrate interaction take place, what are the different inhibitions, all these things, and also we try to analyze the batch process, CSTR and plug flow reactor, and try to find out that what is the time required for batch reactor, what is the time space time required for the CSTR, what is the space time required for plug flow reactor. Now today actually we are going to discuss some problem, because some coming 2 lectures I will be concentrating on different problems that we have involved with different type of enzymatic reactions. Now first problem that I want to discuss, that is a very common problem that we have in the enzymatic reaction, that suppose we carry out any kind of reaction in a vessel. Now question comes that at different time of reaction, what is the percentage of substrate converted? Now how we can find out? Now in my previous lectures we try to develop the correlation between the substrate concentration and time of reaction. That correlation of enzymatic reaction we try to develop. Now in this particular problem we'll see the application of that, how we can apply in the enzymatic reaction. The first problem that I am going to discuss, that is that an enzyme with enzyme with Km 1 into 10 to the power minus 3 moles were assayed using the initial substrate concentration 3 into 10 to the power 5 moles substrate. After 2 minutes, 5% of the substrate was converted. How much substrate will be converted after 10 minutes, 30 minutes and 60 minutes? So in this problem, if you look at what is happening, that we know that this is the Michaelis-Menten equation we already discussed, V equal to V max S Km plus S. Am I right? Now this is equal to velocity of reaction equal to minus ds by dt. Now if from this we can develop this correlation. This is so this correlation, final correlation will be coming this Km that d ln S and ds is 0 to S and V max 0 to T dt. And if you solve it, it will be S 0 minus S Km ln S 0 by S and V max. Now in the problem, what is happening, that Km is given and S 0 initial substrate concentration is given and 5% substrate converted in 2 minutes. So time of reaction is 2 minutes and S value is the 5%. 5% means initial substrate concentration was 3 into 10 to the power minus 5 moles. Am I right? If you multiply it, so how many substrate will be remain after the reaction? Reaction will remain is about 0.95, 5% substrate converted. So we can multiply by 95, we will get the substrate conversion after the reaction is over. Now next is that, so here we from this we can find out the value of V max. We can find out this value of V max, but next problem that we have, that is that we shall have to find out how much substrate converted how much substrate converted in 10, 30 and 60 minutes. So, now we know the Km value, we know the Vmax value, and we have this correlation, am I right? So, what we can do, we can here we can this x is equal to what? S0 minus S by S0. So, we can write in term of x, this is 1 minus S by S0, am I right? So, S by S0 I can write S0 equal to 1 minus x. So, S equal to S0 minus 1 minus x. So, we can convert this term in the form of S0 and x. So, if you can count, then it will x, what is x? X is the nothing but that how much substrate that is converted, S0 minus. So, that is exactly we shall have to find out how much substrate is converted. Now, here we have now we can put the values in this equation, and we can find out through the trial error method that we shall have to find out at what value of x left hand side is required to right hand side, and we find that after 10 minutes that 23% substrate converted. And similarly, if we calculate after 30 and 60 minutes, we will find 54 and the 80% substrate will be converted. So, this is a very common enzymatic reaction that we have, and we can any kind of enzymatic reaction we can analyze and find out how much substrate will be converted at different time of reactions. Now, next problem that I am going to discuss, the following data were given to obtain for a competitive inhibition study, in which I is the concentration of inhibitor and equal to 3 micromolar for the determination of value of V in the presence of the inhibitor. Now, here I want to tell you a very interesting thing that we already discussed. In case of competitive inhibitor, what I told you that this is V and this is substrate, am I right? And this is the no inhibition. When there is no inhibition, then we have this plot. Now, in case of competitive inhibition, this will be like this. So, at infinite substrate concentration, it will be becoming Vmax. This is equal to Vmax. So, we know in case of competitive reaction, Vmax will remain constant, and what Km will increases, and if Km is increases, the velocity of reaction will decrease. So, this is the, so in this problem, so we have this is no inhibition and this is inhibitor. So, you can see the nature of plot is given here. This is inhibitor and this is no inhibition that we have. Now, Vmax is given here, Vmax value is given 200 micromoles per minute for both data set, and determined what we shall have to determine value of Km for the data obtained in absence of the inhibitor, and Km dash for the data obtained in presence of the inhibitor, and calculate the value of Ki. So, 3 different things we shall have to find out. We shall have to find out that Km value without inhibition, and Km dash value with inhibition, and Ki value that what we call inhibition constant, that we shall have to find out. And this is the common feature of any kind of enzymatic reaction, and let us see how we can find out these different values. Now, when you talk about the Km value, we know what you know, that when V equal to Vmax by 2, then your S, the substrate concentration, is equal to Km value, because I can show you that we have V equal to Vmax S Km plus S. Now, when if we assume V equal to Vmax by 2, then what will happen? This is Vmax by 2, am I right? So, this is Vmax by 2 into Km plus Vmax by 2 into S equal to Vmax S. So, I can bring it that side, then we will find the Km is equal to S. So, now what is happening, that in case of enzymatic reaction, that the V equal to V versus S plot is like this without inhibition. Now, we know this is Vmax value. Now, this is half Vmax by 2, am I right? So, this is this value at this substrate concentration, this is equal to Km. So, we can easily find out the Km value from this particular plot. This is exactly what we have done here, that you know that this is no inhibition, this is no inhibition. Now, in case of no, and this is Vmax, and there is 200 is the 200 micromoles per minute is the Vmax value, and so half of this is 100, am I right? So, this values, what is this value? This is equal to 10. So, this is exactly, this is the 10 micromoles. What will be the Km value? That in this competitive without inhibition, that is the 10 micromolar. Okay. Now, let us see in case of the inhibition. When inhibition, that we have the plot is like this. This is the inhibition plot. Now, here that half of the inhibition, because we know Vmax is constant, because in case of competitive inhibition, Vmax is constant, am I right? Now, if this is constant, then this corresponding value here, how much is coming? This is 30 micromolar. This is exactly what we have written here. So, with inhibition, the Km value will be 30 micromoles. Without inhibition, it should be 10 micromoles. Now, next is that we shall have to find out the value of Km. So, in case of competitive inhibition, we know the Km dash equal to Km into this, because we can remember that we have shown this equation in case of competitive inhibition. Vmax S Km 1 plus I by Ki plus S. Am I right? I told you when I equal to 0, it will be becoming the Michaelis-Menten equation. So, this is actually the Km dash value. This is equal to Km dash value. So, we have already calculated the Km dash value is 30 micromoles, and Km value how much we have calculated 10 micromoles. So, this we can write 30 micromoles, 10 micromoles in this equation. That inhibitory concentration is 3 micromoles, that is given. So, we can easily calculate the Ki value. Ki value is nothing but that equilibrium constant between the enzyme and the inhibitor complex, that that is the equilibrium constant. This is Ki value, we can easily calculate. So, in this particular problem, what we try to find out? We try to find out that in case of competitive inhibition, how we can determine the value of Km, how we can find out the new Km value due to inhibition, and from this Km value, we can also determine the value of Ki, that is the equilibrium constant between the enzyme and the inhibitors. Now, next problem. Next problem is also very interesting. If you look at a series of experiments were performed to determine the Ki values for 3 competitive inhibitors. So, the following tables listed results are like this. this A inhibitor, B inhibitor, let us assume the 3 different inhibitors and they are competitive in nature and their Ki value is different. One is 1, one is 5, one is 1, another is 0.012. Now, what we shall have to find out, which inhibitor binds with higher affinity with the free enzyme, this we shall have to determine. If the same concentration of inhibitor were used for each experiment, which inhibitor would give the smallest value of Km dash, that we shall have to find out. And if the value of Km is 1 micromole, what is the ratio of Ki by Km of the each inhibitor, and how this related in the competing equilibrium for binding substrate versus the inhibitor to the enzymes. So, what is the we know that during discussion discussing this competitive inhibitor, we come across different type of competitive inhibitor. You might be knowing that one is completely competitive inhibition and that is partially competitive inhibition. Now, in case of completely competitive inhibition, both inhibitor and substrate, they compete for the same active sites of the enzyme. But in case of partially competitive inhibition, the inhibitor compete other than the active sites of the inhibitor, so that it makes some kind of conformational change of the active site, so the substrate cannot interact with the enzyme. So, this is that kind of things we want to find out, how they compete with the active site, same active site that we are going to sort out here in this problem. So, the first solution that if you look at that the first question that was like this. First question was the which inhibitor binds higher affinity with the free energy. That we have 3 inhibitors at different Ki value, where one is Ki value is high and the low and this. So, we know since it is competitive inhibition, again let me write Km equal to what? Km dash equal to what? Km plus I plus Ki. Am I right? So, this is the equation that we have. Now, the question is that if I value is the inhibitor with lowest value of I binds the highest affinity. So, the inhibitor C, that is the why if the I value is very low, then what will happen, this value will be high, and if this value is high, your inhibition will be more. So, since Ki value in case of third inhibitor is Ki value is lowest. So, we can always say inhibitor with the lowest Ki value binds with higher affinity with the active sites of the enzyme. And so, if you look at the second, the smallest value of Km value implies the weakest binding of inhibitor, the least amount of E. The inhibitor A would give the lowest value of Km dash. Obviously, if this value is high, then this value will be lowest. If you look at A, B, C, 3 inhibitor we have given in this problem, we have find the A has higher value of Ki. So, if the higher value of Ki is there, then in this case the Km dash value will be low. So, I can always say that the smallest value of Km dash value implies the weakest binding of inhibitor or least amount of competition with enzyme and inhibitor A, which will give the lowest value of Km. Now, third part is very interesting, that ratio of Ki and directly compares the binding constant both inhibitor and substrate. Let us take the example. Now, Ki, if Ki by Km ratio is very high. Now, Ki is very high as compared to, then what will happen, the substrate binds tighter, because Ki is very high, then this will be very low. Am I right? Then substrate will bind with the enzyme. So, inhibition will not have much effect on the kinetics. So, substrate binding with the enzymes will be more. So, this is very clear. and when Ki by Km is equal to 1, then this is the situation where the substrate and inhibitor binds with the same affinity, because then they are competing in the same way, that when Ki by Km equal to 1. But when Ki and Km is less than 1, then what will happen, that then Km will be higher as compared to Ki. So then what will happen, the inhibitor binds greater affinity, and so the stronger inhibition occurs in the kinetics. So this is very clear, because the clear cut idea that we have now, how Ki and Km contribute in the inhibition of the enzymatic reactions. In this case, Ki by Km 5, 1 and -2 for ABC respectively. Thus, as was in case of inhibitor C binds with greater affinity and will have the greater effect kinetics than AB. So you know that, so this is clear from this, that the inhibitor C had the greater affinity, and that and will have the greater effect on the enzymatic kinetics. So I hope this problem gives you how the inhibitor takes part in the enzymatic reaction and affects the enzyme inhibitor interaction, enzyme substrate interaction, how it affects. Now next problem, I told you when during my presentation that one of the application that we have in the this inhibition of the enzymatic reactions, what is the application that we have? I told you that for the determination of complex organic molecules, which is very difficult to estimate in the normal analytical techniques. I have given the example of pesticides. Pesticides are very complex chemicals, and these pesticides usually we estimated with the help of HPLC. HPLC, we know that is a very sophisticated instrument. Now, by using this enzymatic reaction kinetics, it is possible to determine the concentration of pesticide. Now, this particular problem deals with that how one pesticides inhibits some kind of enzymes, let us assume A, and how this the inhibition helps you to find out the pesticide concentration in your sample. So let us go to this problem. Now here the pesticide, the problem is given, a pesticide inhibits the activity of a particular enzyme A, which can therefore be used to assay for the presence of the pesticides in the unknown sample. This is a way, because I told you, besides that I told you that inhibition has also greater role to play in the medicinal sector, because I told you that for the production of sulfur drug also this enzyme can be largely used, and also some other purpose also it can be used. Now this is pesticides, this problem deals with how the pesticides concentration can be determined. Now in the laboratory, the initial red data is shown in the table were obtained, and is the pesticides a competitive, non-competitive inhibitor, and evaluate the value of Ki, Vmax and Km. So you know that here I want to tell you that we have already discussed that competitive inhibition, and competitive inhibition, how we can find out the competitive inhibition nature with the help of Lineweaver-Buck plot. What is the Lineweaver-Buck plot? This is nothing but 1 by V versus 1 by S. Am I right? So if you have V, this is the Michaelis-Menten equation, S Km plus S. Now if you write 1 by V, then we can write Km by V max equal to 1 by S plus the 1 by V max. Okay. Now here, so in case of no inhibition, this is no inhibition. In case of no inhibition, you have this plot, am I right? But we know from this equation we know the slope is nothing but equal to Km by V max, am I right? And this intercept is 1 by V max. Now, in case of competitive inhibition, this will be what? This will be like this, where 1 by V max will be intercept, the point of intersection will be same, but slope will be different, and this V max is constant. So, so what we shall have to find out? We shall have to in this particular problem, we can in this particular problem we can find out that what is the nature of plot, and from the nature of plot we can find out whether the nature is coming the line over Bach plot. If it comes like this, sorry, this not this should go through the point of intersection is like this, then we call it competitive inhibition. But in case of non-competitive inhibition, situation is different. This here it will be like this. So, this point of intersection this point of intersection, that will be different. This V max, so this V max and this V max. So, this V max in case of inhibition, competitive non-competitive inhibition, this will be higher. Since 1 by V max is higher, then V max will be smaller. So, will be smaller. Okay. In case of non-competitive inhibition, that we can find out. So, this way, that is exactly we shall have to do from this problem, that we shall have to find out that what is the nature of the slope, and from this slope we can find out whether it is competitive inhibition, what is non-competitive inhibition. Now, in case of competitive inhibition, we know the equation, rate equation, and we know in case of non-competitive inhibition, we know the rate equation. So, if we use that rate equation, then we can find out the value of Ki, V max and Km. This value we can easily calculate. Now, second problem is very interesting. The second part, what is saying that 50 milliliter of the same enzyme solution of part A mixed with 50 milliliter of the substrate and 25 milliliter of the sample. The initial rate observed, that is the 18 millimoles per liter per minutes. What is the pesticide concentration of the unknown sample, assuming no other inhibitor or substrate present in the sample? Now, what does it mean? Because let us try to understand. What is saying that 50 milliliter of the enzyme solution, am I right? Enzyme solution. Same enzyme solution is mixed with 50 milliliter of substrate, am I right? And 25 milliliter of sample. Sample means pesticide sample. So, what is the total volume is coming? 125 milliliter, am I right? So, when we use this enzyme solution, what will be dilution we have? The dilution is 50 by 125. So, whatever activity we have, that is to be that concentration we have, substrate concentration we have, that is to be multiplied by this factor, then and only then we will get the exact substrate concentration, and then we can find out the exactly what is the inhibitor concentration. Let us see how we have solved that. Now, in this Michaelis-Menten equation, in the line over Bach plot, we have 1 by V equal to 1 by V max, Km V max is this like this. Now, when we plotted in this graph paper, we have come across this kind of plots. Now, this is with inhibition, this is this colored indicate this is inhibition, and this is without inhibition. Now, it is clear from this graph that this is the example of competitive inhibition. Am I right? This is the example of competitive inhibition. So, in case of competitive inhibition, what is the equation we have? V equal to V max S Km 1 plus I by Ki plus S. Am I right? So, now our situation is very simple. From this interaction, we can easily find out the this no inhibition, we can find out the value of V max and Km, and from this interaction we can find out the new Km value, and once we Km value we find out, we can easily find out, because this is the Km dash value. This is Km dash value is equal to what? Km plus 1 plus by Ki. Am I right? Now, here this is the we can directly find out, this is 1 by, this is with inhibition, we can find out this is 1 by Km value, this is, and with inhibition, this is without inhibition. So, we do not have to calculate from this directly from the graph, we can have these values and put it and find out the value of Ki. Ki is not very difficult to estimate. Now, then the next part as I told you, the last part is very interesting, that you have to find out what is the pesticide concentration. Am I right? Now, in the substrate concentration is given here, but only the thing is, this is the substrate concentration and this will be multiplied with the dilution factor 50 by 125, then we will get this, and then velocity of reaction is this. Then we put this in this equation, we find this equation, we know the value of S, we know Km, V max value, Km value, Ki value you know. So, S value you know, so I value we can easily find out, and we find I value is this. So, this from this equation, but actual pesticide concentration will be what? Actual pesticide, if we find out from this I value is this, actual pesticide, actual value of pesticide side will be what? This will be 3.77 into 10 to the power minus 5 m into 125 by 50. Because why we have multiplied by this factor? Because initially the because your pesticide solution also diluted. Am I right? So but no, I did the mistake. In case of pesticide, the dilution factor will be little bit higher, because we have used the 25 milliliter. Am I right? So, 25 milliliter means this is to be multiplied by 25. Then you will get the exact pesticide concentration that we have in the sample. So, this is how we can easily find out that the concentration of pesticide in an unknown sample. So, today in this particular lecture we try to cover that how we can find out that the substrate concentration at different time of reaction. Then we have done some kind of detailing on that, how the interaction between inhibitor and substrate can be determined with the help of Ki values, different type of Ki value, and finally we try to find out how the concentration of pesticides can be determined with the help of enzymatic reaction. Thank you very much.